My name is Sean Bergen, and I'm a member of the ComSysNet educational team. In this video, I'll discuss the importance of analyzing the output from your agent-based model and review some of the techniques one might use to analyze the results. Agent-based modeling offers practitioners an approach that can integrate knowledge and questions from a range of disciplines. From biology to social sciences or from physics to archaeology, scientists can integrate data from a wide range of sources or ask questions that are difficult to address with other approaches. Agent-based models allow for an explicit representation of almost anything and their relations, distributions in space, while including complex heterogeneous behavior. As an approach, agent-based modeling is continuing to define standards of practice and documentation, yet often the most difficult component of creating an agent-based model isn't deciding on your question or even coding your model, it's analyzing the output from your model. Agent-based models continue to increase in complexity as computational power and availability has continued to advance. Of course, as these models have become more complex, so does analyzing their output. But before one begins to analyze the output from their agent-based model, one has to account for stochasticity. Most agent-based models include some sort of randomness or stochasticity. Stochasticity is often used to represent variation in a characteristic that may affect a model, but is unknown. Stochasticity can also be found in agent properties, spatial locations, model processes, and model parameters. Stochasticity is often present in the creation of agents. Agents may have a random age, or have random amounts of money, or there can be random numbers of the agents. Network connections may also be random, even though qualities of a network remain fixed. Spatial variation is also another common source of stochasticity. Let's consider a model of herbivores and lions in Africa. As a researcher, I don't know where an animal will be at a given time, but I do know an approximate density. So the same number of animals are randomly distributed across the landscape each time the model begins, even though I'm using the same density numbers. Model processes are often a forgotten source of stochasticity. For example, when agents are asked to perform an action in your simulation, many programming languages ask each agent to do that action in a random order, which changes each step of a model. Or if you're selecting one agent from a group of agents to perform an action, that selection is also a source of stochasticity. Finally, model parameters that a researcher sets are also an important source of stochasticity. The model parameters that you use to start a model are rarely fixed. They can be used to affect the outcome of your model as well. These different parameter combinations are also an important source of variation. The inclusion of stochasticity within the agent-based model usually means that running a model multiple times will produce different results. To illustrate that point, let's look at a simpler example, the example model Fire in NetLogo. In the model, fire begins on the left side of the screen and spreads to neighboring patches. The spread of the fire is affected by the density of the trees. But we can use the same tree density and get a different result. So, if the model does not always yield the same result, then how do we know that we can trust the model's outcome? One can, of course, average multiple model runs together, but how do we know that our average is representative? How do we know how many times we need to run the model? This type of analysis is called sensitivity analysis. Sensitivity analysis can help us better understand the robustness of findings gained within a model. Sensitivity analysis can also help us identify which model parameters or inputs affect the variability of model results. For example, if small modifications of model input produce widely different results, then we are able to identify more important processes. And of course, the opposite is true. We may be able to identify inputs which have minimal importance to our model's outcome. we may focus on identifying the most accurate value for an input because of its importance to the model's results. Unfortunately, there is not a single approach to sensitivity analysis that can be followed by all researchers. As argued by Ligman, Zielinska, and colleagues, the type of sensitivity analysis you conduct on your model is determined in large part by the model you're working on. An agent-based model may range from a simpler or more abstract model to a highly complex model with a vast number of inputs and outputs that is being used to understand social or economic policy. In the case of less complex agent-based models, simpler sensitivity analysis methods may be sufficient for capturing the dependencies between inputs, while in the case of data-driven complex models, more sophisticated sensitivity analysis approaches may be required. One group of approaches which we will briefly review involves looking at the mean and variance for one output. We will use the FIRE model from NetLogo again, which has one input parameter, the density of trees, and the model outputs the percent of the forest burned. The main source of stochasticity in this model is the random location of trees, which is remade every time the model is initialized. Let us suppose that we wanted to know how many times we should repeat our model to be confident of the results. Our first approach is to look at the cumulative mean. On the x-axis, we have the number of simulations, and on the y-axis, we have our output value, the percent of trees burned. This approach shows that the mean value of one simulation, two simulations, and three simulations, and as you can see, the more simulations we add to our sample, the less variation, the less wiggle we see in our mean value. Using this graph, we can see that we are not going to gain much running the simulation 5,000 times instead of 3,000. We might decide that there's a minimal variation by 2,500 or 2,000. And we can also see that there's a lot of variation with just a sample of 500. A very similar approach is to look at the cumulative variance. Again, our x-axis is the number of simulations, ranging from 0 to 5,000. Here we see that the variance is low by around 2,000, although it looks very low at 4,000. Running our model 4,000 times for each parameter value isn't ideal, but if we have a fast agent-based model, then it might be feasible. A useful approach is to look at the change in the coefficient of variance. This can be calculated by subtracting the coefficient of variance at each simulation run to measure the effect of adding more simulations to your sample. Here, we see that while there is some variation, we will have a reasonable level of error if we only run our model 2,000 times. Now, this graph is only for one parameter value and one output. We should still compare other parameters to see if our sample size of 2,000 looks to be enough. We may also need to test other outputs to see if they produce similar results at a size of 200 or if a different sample size will be needed. Instead of only testing a tree density of 55%, here we see the cumulative means of two other values of that parameter, 25% tree density and 75% tree density. As you can see, both of these measures indicate that less than 1,000 model runs are needed, and perhaps only 500 to capture any stochasticity in the model. In this case, this is the result of how the model works. At very low densities, the fire does not spread far, and at very high densities, almost all of the trees are burned. This illustrates why it is important to test multiple values of a parameter, and probably even multiple combinations of parameters, to understand the variation in output which can occur from your model's stochasticity. As I mentioned before, this is just one of many ways to conduct a sensitivity analysis on your model. Complex models will likely require more sophisticated approaches, and agent-based modelers continue to approach model analysis in new ways. Please refer to the resources below to learn about other model analysis techniques.